This video will help you understand how the HTTPS protocol works. We do not cover the HTTP protocol itself, the protocol used when a web server wants to communicate with a browser. This video describes how the HTTP protocol has a security layer placed over it to make it secure, thus becoming the HTTPS protocol. We'll cover some key terms such as encryption, symmetric encryption, asymmetric encryption, hash values, digital certificates, digital signatures, authentication, phishing, and pharming. We already know what a phishing site is, a website that looks like a legitimate site but is in fact fake and is trying to steal your personal information. The giveaway here is the URL in the address bar. Although it says PayPal, we should realise that this is a subdomain as the www is missing from the URL. Anyone with a website can create a subdomain on that site and call it anything they want. The fact that it has a different domain name before the top level domain, the .com part, in this case moneyfraudster.com, lets us know that this is not really PayPal. In real life, fraudsters usually have long random domain names, so people will just think it's one of those really long addresses that doesn't make sense to them anyway. This, however, is a pharming site, and this is much more difficult to spot, if at all. The URL in the address bar is right, but there is one important detail missing. There's no S on the HTTP protocol at the start of the URL. This page, in fact, still belongs to moneyfraudster.com, and is going to steal your PayPal login and then your money. So how does pharming work? That URL in the address bar is not an actual address. Computers use IP addresses, a string of numbers, to identify them. This string of numbers is very difficult for humans to remember, so we give them domain names. When you enter a domain name into your browser, the browser passes it to your internet service provider. Your internet service provider has a database of URLs and their matching IP addresses, which it can search. When it finds the URL, it gets the matching IP and sends it back to your web browser. Now that your web browser has an actual address, it can go straight to the web server on the internet and request the web page that it wants. Your computer also keeps its own DNS database in its internet history in case it wants to revisit the same web pages. This means it doesn't have to keep going back to your ISP to get IP addresses that it has already retrieved. Each time your browser gets a domain IP address, it updates its own DNS database. But Money Fraudster is back and wants to attack your DNS database. If he can hack the ISP DNS database and overwrite a bank's IP address with one for a computer that he controls, or more likely a DNS database on your personal computer, then any web request we make to www.piggybank.co.uk will be sent to Money Fraudster and not the real bank's web server. This is why all banks, financial and e-commerce websites use HTTPS. Even sites that don't hold any personal or payment information are moving to HTTPS, because this adds strong security features to any communication that the website in the form of a digital authentication and encryption communications. The HTTPS protocol has two stages. First, the user's browser will authenticate the web server it is talking to by requesting a copy of its digital certificate. The browser will then check if the certificate is authentic. If our DNS has been farmed and the browser is talking to a fake web server, the certificate will not authenticate and the connection will be dropped. If we get a certificate from a genuine server, then the certificate will authenticate and we move on to the next step. The second step is for the browser to share its public key with the authenticated server and set up a secure communication link where all of the normal HTTP messages will be encrypted. If you are taking notes, exam notes, you will want to pause at the end of this slide and write down the following 6 things that are included on a digital certificate. Certificate authority is identified. The domain name owner is identified. The domain owner's public key is on the certificate. Issue and expiry dates for the certificate. Then 2 signatures, first the domain owner's signature and also the certificate authority signature. In order to understand how the authentication of digital certificates happen, there are 2 things we first need to understand. The first is encryption, specifically asymmetric encryption, and the second are fixed length hash values. Let's start with the hash values. A hash generator is a mathematical function that turns any input value into a fixed length output value. The input can be anything: a computer program, some text, a movie file, or any other type of file or data can be input. The result will be a fixed length value. Fixed length means we know exactly how many digits or how long the result will be, and it's always the same length, i.e. it's fixed. It doesn't matter how big or small the input value, the output is always the same length. I entered a sentence into an MD5 hash calculator and received a 32-bit hexadecimal number. Hex numbers include the letters A to F. I then entered just 2 letters and also got a 32-digit output. Finally, I input the poem If by Rudyard Kipling, and you guessed it, another 32-digit output. Note, each time you input the same data into an MD5 generator, it will always generate the exact same 32-digit value, and the probability of 2 different inputs generating the same output are so small that it is almost impossible, but not quite. So we could regard these values as virtually unique. If you change anything, even one letter change from uppercase to lowercase, in this case the D in digital, and you'll get a completely different hash value output from the hashing algorithm. Hashtags are used in lots of digital situations as a way to prove that an electronic file has not been modified or tampered with in any way. Looking at the hash values produced here, we don't know what has been changed from the first 2 sentences to the third, but we know that something is different. Now let's look at encryption. Encryption is just another mathematical function, but this time it turns our data known as plain text. We call it plain text because it is the data that we can read and understand. And it turns this into, well, gibberish, a text file that has no meaning to us at all. This gibberish is really a secret code that only some of us can understand. To understand the encrypted file, we need to know the secret or the key to unscrambling the data. If we have that key, then we can run our encrypted file back through a similar function known as a decryption, which unlocks the file and turns it back into the plain text again so that we can understand it and use it. Asymmetric encryption is a type of encryption that uses 2 matched keys known as a public and private key pair. The keys work in pairs and one is of no use without the other. The public key is used to scramble the plain text into the encrypted file, whereas its matched private key is used to descramble the encrypted file back into plain text. Let's take a look at how this can be used in real life. If 2 computers want to have a secure conversation on a network, such as the internet, then they must first generate one of these key pairs. The private keys shown here in white are kept safe inside the computer and never shown to anyone else, hence private. The public keys, on the other hand, are shared with anyone who wants to communicate with that computer. Each computer now has their own key pair and the public key of other computers that it communicates with, and they keep these inside a table on the hard drive known as a key chain. If a computer A wishes to send a message to computer B, then it uses computer B's public key to lock or encrypt the message before putting it onto the network. The encrypted message is then transmitted across the network, where computer B uses its private key to unlock the message, i.e. decrypt it back to plain text, and it can then read its contents. Here comes the money fraudster to try and steal our precious data. Remember, this could be credit card information, personal data, or anything being transmitted over to computer B. Money fraudster already has a copy of both public keys, because remember, we give these out to anyone who wants them. If money fraudster managed to grab a copy of the message as it was being sent, it is still of no use to him, as it is encrypted and he doesn't have the key to turn it back into plain text. He could try using the public key of the computer sending the message, but that won't work. He could even try using the key that encrypted the message in the first place, but that won't work either. The private key stored safely on computer B is the only thing that will unlock this message. So, now that we understand hash values and asymmetric encryption, let's look at how digital certificates work and how they allow a user's web browser to authenticate a web server. Of course, it's also important to understand that digital certificates are just that, digital. They're not a paper certificate. They are a computer file. In fact, they're actually a collection of computer files. There is the certificate itself. Attached to the certificate is an encrypted file, which is the authority signature file, and lastly another encrypted file, which is the web server's own signature file. The certificate itself is just a data file created by the certificate authority holding specific information such as the web server's identity, its public key, a tag identifying the authority itself, dates and some other information. So where do we get the encrypted signature files from? Let's look again at those key pairs we saw in asymmetric encryption. When a pair of keys are generated, one key is not preset as the public and the other private. You just pick one to share and one to keep secret. And it really doesn't matter which is which. If we want to encrypt a message to keep it secure, then either key can be used to do the encryption or the locking. As long as we know which key was used to encrypt the message, we can use the other key to unlock or decrypt the message back to its plain text. These keys literally work in pairs. And no, you cannot mix and match pairs. It's like the number bonds you may have done in primary school. 7 and 3 go together to make 10, 6 and 4 go together to make 10. But if you take 6 from one pair and 3 from the other, then it just won't add up right. Let's use what we know to create the digital signatures that we want to attach to our digital certificate. Well, as it is the digital certificate itself that we want to authenticate, that is, make sure it is genuine and not modified in any way, i.e. a forgery, we start by running it through a hash calculator algorithm, and it generates this pseudo-unique value. Remember, if we put our certificate through the same generator function, it will always generate the same unique hash value. Any computer can perform the same calculation and generate a hash from the certificate they have been given. If the computer generates the same value, then we know the certificate has not been modified in any way. If it calculates a different value, then the certificate has been tampered with by someone and it is not authentic. To create our signatures, we use asymmetric encryption to encrypt the digital certificate's hash value that was generated from the certificate. Unlike communication encryption, this time we use the private key to lock the file. Why? Well, in this case, we're using the digital authority's private key. This key is secret and known only to the certificate authority themselves. So, only the real certificate authority can generate this specific encrypted file using its private key. The file is the authority signature and is unique to this authority and this certificate. Next, we plug in the web server's private key, run the certificate through the encryption function and generate a unique signature file for the website owner. We now have two signature files that are unique to this digital certificate, one using the certificate authority's private key and one using the website owner's private key. Now, if Money Fraudster tried to use HTTPS, when our browser requests a certificate from him, the browser will quickly realise there's something wrong with the certificate and drop any communication with that server. If our browser starts a HTTPS communication with the genuine web server, it will quickly authenticate the genuine digital certificate and continue with the encrypted communication using the server's public key, which, as we know, is contained on the digital certificate itself. So exactly how does this authentication take place? As you may have already worked out, we reverse some of the procedures we used to create the signature in the first place. To do this, our web browser needs three things: the web server's public key, the web server's digital signature, and finally, the certificate itself. Authentication is all based around hash values, so the first thing our browser must do is calculate the hash value for the certificate that has been given. The browser now has a known value for the certificate and puts it to one side for the moment. The browser now needs to decrypt the website server signature. Remember, the file was encrypted using the web server's private key, so the only key that can decrypt it is the web server's public key. The decrypted files now reveals the original hash value for the digital certificate. The browser can now compare these two values to see if they match. If they do, then the only one who could have generated that signature is the website that owns the matching private key to the public key contained on the certificate. So why then do we need two signatures on a digital certificate? Let's bring back the Money Fraudster. He has used the web server to generate a new pair of keys of his own. He has also got a copy of the genuine digital certificate from anyone who communicates with the genuine web server is given a copy as part of the authentication process. Now, he could just give the certificate to anybody who asks, and it will look like he is the genuine web server, but there is one big problem with that. The certificate has the public key, seen in green here, of the genuine web server and not Money Fraudster's web server. Money Fraudster does not have the matching private key to that. So, when our browser encrypts the data using that green public key and sends it to Money Fraudster, he cannot decrypt it back into its usable plain text format. Money Fraudster needs to change the certificate and put his own public key in place of the genuine one, so that he is able to decrypt any messages he receives. But he then also needs to create a new signature to attach to the certificate. To do this, he needs to run the certificate with his public key through the hash generator and create a new hash value. Then pass this hash value into the encryption algorithm using his own private key to lock it. This creates a new signature, which he attaches to the certificate. When our web browser comes along and tries to authenticate the new signature, it will pass the authentication process even though the certificate is fake, as the new signature matches the new certificate. But before setting up the encrypted communication with the web server, your computer's web browser will want to authenticate the certificate authority signature as well. The web browser has already got the hash value calculated from the new certificate. It now takes the authority signature and passes it through the decryption algorithm using the authority's public key, which reveals the plain text hash value that the certificate authority generated from the original digital certificate. Your web browser will then compare the two hash values and see that they don't match. Your web browser now knows that the certificate has been given is fake and drops the communication with money fraudster's dodgy web server. So if money fraudster can fake the certificate and the owner's signature by creating his own key pair, why can he not fake the authority signature as well with another key pair? Certificate authorities are companies that check a website owner's real world identity and then provide a certificate for the digital world. Each of these companies have their own public-private key pairs, and of course the private keys are kept secret. However, the public keys themselves are not shared online. They are hard-coded into all modern web browsers. This means there is no way for money fraudster to switch out their public keys with one of his own, as your browser already has that key. Simply put, this means that money fraudster cannot use the HTTPS protocols on his dodgy web server. If he wants the two signatures to authenticate, then he must leave the original certificate unmodified. But it contains the genuine web server's public key, and he cannot decrypt those messages, making them useless to him. If he changes the certificate to get his own public key on there, he can forge the owner's signature, but the authentication will then fail on the certificate authority signature. Now that we know how authentication happens, let's take a closer look at the encrypted communications channel that is set up between your computer's web browser and the web server. We already know about asymmetric encryption, key pairs, and the trading of public keys, but there is a much simpler option. Symmetric encryption uses one shared key which does both the encrypting and decrypting of the plain text files. This key is generated by one of the computers in the communication and then shared with the other. We see the problem now. The key can be easily intercepted as it is being shared. Now all money fraudster has to do is to spy on our communications, and he is able to decrypt every communication between your browser and the bank's web server. But symmetric encryption has one real benefit. It takes much less processing power to do the calculations needed for encrypting and decrypting. Less processing means much faster communications. When we authenticate digital certificates, this relies on the use of asymmetric encrypted key pairs. Anyone can have a copy of these public keys, including money fraudster. But things will be much faster if we use a symmetric encryption single shared key. There is a clever solution to this. A computer can now use computer B's primary key to encrypt the shared symmetric key itself. This encrypted version of the key can then be safely transmitted to computer B. Computer B can now use his own private key to decrypt the file back into a copy of the shared asymmetric encryption key. And even if money fraudster did intercept this communication, all he has to show for it is an encrypted file that he doesn't have the key for. Following the authentication of digital certificates, HTTPS uses asymmetric encryption to secretly generate a shared key, and the remainder of the communication is done through the much faster symmetric encryption method. Time to get your notebooks out. Pause each of the next 5 slides at the end and use them to make notes. There will be slides on encryption, asymmetric encryption, digital certificates and digital signatures, authentication, and the final slide will be the HTTPS protocol itself. Remember, these are mark scheme notes that highlight key mark points in an exam question. For better understanding, you should expand on these notes, going back over the video or other research as needed. Encryption. Data or plain text is scrambled into something meaningless before transmission over a network, so that if it is intercepted by a criminal, it will be useless to them. Only someone with a decryption key algorithm can reconstruct the encrypted message back into plain text so that it becomes useful. Asymmetric encryption. Keys are used in matching pairs. One is of no use without the other. One key is used to encrypt plain text and the other to decrypt it, and these are interchangeable. One key is made public and the other is kept secret or secure on the owner's network. The second party uses the first party's public key to encrypt messages that are sent to the first party and vice versa. Only the owner of the public key has its matching private key and is able to decrypt messages intended for them. For two-way communications, both parties must share their public keys. Digital certificates and signatures. Digital certificates are created by a certifying authority or company on behalf of a website owner. It uses the owner's own public key. Hash sums are generated from the certificate. The hash sum is encrypted using the authority private key, so it can only be decrypted by their public key. The encrypted hash value, the authority signature, is attached to the certificate. The owners use their own public key to encrypt the same hash value, which is the owner's signature, and this signature is also attached to the certificate. Digital authentication. When a digital certificate is received by a web browser, the browser generates a hash sum for the certificate. The browser decrypts the authority signature using their public key, which is hard-coded into the browser. The browser decrypts the server owner's signature with the public key on the digital certificate. If both decrypted signatures match browser's calculated hash sum, then authentication passes. Otherwise, it fails. HTTPS. This is the HTTP protocol along with the additional secure socket layer SSL. The user's browser requests digital certificates from a web server. The web server passes the signed digital certificate to the browser, and the browser uses the public key of the owner and the authority to authenticate the digital certificate. If the authentication passes, the user's browser will generate its own public private key pair just for this interaction, and then share the public key with the web server. The public keys are then used to encrypt the messages used to create a single symmetric shared key for faster encrypted communication.